We're down to our final two presentations now. So I'd love to have Nicholas V. I'm not going to try and pronounce your last name, Nicholas, who was mentored by Mike Stamatikos. Mike, would you like to introduce Nicholas?
Yes, my pleasure. Nicholas Vasilescu, I had the pleasure of working with this summer. He hails from the Big Apple, New York City, and he is from the largest public STEM high school system in the United States. That's the Brooklyn Technical High School. I'll let him talk about his project, which features a joint analysis of IceCube and SWIFT data. So looking at neutrino astronomy and gamma ray bursts. These are buzzwords now in astronomy. It's at the vanguard of research. Time domain astronomy, multi-messenger astronomy is really huge. So I was very happy that he was able to tackle this project, and I was very impressed with what he was able to accomplish. And I want to wish him well as he's going to start his physics career as a physics major and a history major at Cornell University, which is very impressive. So I will give the floor to Nicholas.
Thank you very much. Should I share my screen?
Go ahead.
Can you see my screen?
Yes, your slides are just loading for a second.
Not quite yet. It still says loading. Are you in a place with slow internet?
No. Maybe I just shared my Safari.
Did you also send the slides to Iriana? Oh, there we
Yes.
go. Yeah. All right, we're good.
Can you see it or? Okay.
Yes, it's there now, but you're not in slideshow mode, so you probably switch to the app.
Yeah, can you see it?
On that
The loading thing again.
Oh, maybe when I present it.
Let's see.
You could share your screen area.
Okay.
Yes.
Let me pull them up.
Share.
You sent me a PDF, but I can make it reasonably full screen. Okay, here we go.
There.
Yeah,
Hello, everyone. Yes. Hello, everyone. My name is Nicholas Vasilescu. I worked with Professor Stamatikos of Ohio State University, and my project's about tracing neutrinos back to a gamma ray burst using data from IceCube and SWIFT. Next slide, please. So what are we dealing with here? A gamma ray burst is a highly energetic radiation released during a compact binary merger or stellar core collapse from a black hole or neutron star. A neutrino is an electromagnetic neutral particle with an incredibly low mass. We're talking about a mass that's hundreds, if not 1,000 times less than that of an electron. And so these properties allow neutrinos to escape from environments opaque to photons. And so this makes neutrinos incredibly difficult to detect. Next slide, please. And so how might a gamma ray burst in a neutron be connected? So a black hole or neutron star created by a GRB could rapidly rotate, which creates a remnant object that emits relativistic jets. And so these jets dissipate kinetic energy through shocks, which causes electrons and protons to be accelerated, as you could see in the internal dissipation part. And so as a result, these electrons emit gamma rays, which interact with accelerating protons, which create neutrinos that we could observe. Next slide, please. Oh, sorry, maybe it came out. So I got my neutrino data from the IceCube Observatory, which is a neutrino detector that takes up a 1 cubic kilometer space below the surface of the South Pole. And so why create this large detector under the South Pole? It's because it's shielded from the natural radiation from Earth's surface. And so this detector is composed of 5,000 digital optical module sensors that are spread out through 86 kilometer long direct object modules, which are these long rods. And so I used neutrino data from IceCube from April 2008 to July 2018. Next slide, please. I got my GRB data from the Swift Observatory, and this is a satellite in space that detects GRBs with 3 major instruments. The Burst Alert Telescope, which locates the general area a GRB comes from, UVOT, which monitors the afterglow in ultraviolet and visible light, and then the X-ray telescope, which monitors the afterglow in X-rays. And I highlighted my BAT because that's the data that I used. As you could see, BAT's field of view looks less precise than the others, which is true. However, all of Swift's field of views are much more precise than IceCube's. And I used BAT data from December 2004 to July 2023, covering the span of the IceCube data as well. Next slide, please. And so what did I do with the data? I explored if I could trace back neutrinos to a particular GRB, as both data sets provided declination, which is the terrestrial latitude, right ascension, which is terrestrial longitude, and detection time. So in IceCube's case, it's modified Julian date, and in Swift's case, it's standard UTC time. And so the idea is that I attempted to match where in the sky neutrinos and GRBs could potentially arise. And in order to keep my units for time constant, I converted IceCube's data from modified Julian date to UTC time. Next slide, please. And so with a Python program I created, I went through 1,600 Swift GRB files and IceCube neutrino data to look for data with declination and right ascension values that are within 10% of each other. And so realizing that I got a lot of matches, I narrowed the precision down to 1%. And with this method, I found 11 such matches between the IceCube and neutrino data. Then I considered date, which resulted in me finding only 2 GRB and IceCube files that have DEC and RA values within 10% of each other. And so in this table, you could see 11 of those matches using a precision of 1%. Next slide, please. However, I failed to consider T90 time. And so T90 time is important because one cannot be exactly certain how long it takes for neutrinos from prompt gamma ray burst emissions to be detected by IceCube. And so I considered the T90 time measured by Swift. And so what is T90 time? It's the time during which 90% of the photons have been detected during a GRB. And the first and last 5% of photons emitted is omitted to limit possible error, as you could see in this chart. And I thought of T90 as providing like a possible time frame that that it takes for neutrinos to travel from a gamma ray burst to the detector under the surface of the South Pole. Next slide, please. And so the time given in Swift data was actually given in its trigger ID. So you may have seen this particular GRB trigger ID earlier in the presentation as GRB 221009A is the brightest gamma ray burst ever detected. And its date is given in its ID. So the first number provides the year and then the month and the day. So this particular gamma ray burst was the first one detected on October 9th, 2022. And so this code shows how I was able to convert that into standard time. Next slide, please. So I compared the time and sky location. So this for loop compares the particular GRB data to each IceCube data, looking for the same time and then comparing the right ascension and declination data. And then if you notice at the very bottom of this section of code, there's an if statement. So I looked for if the time is in the T90 range for a GRB, and if the RA and DEC data is within 10% of the same data in the GRB, then we have a match. Next slide, please. And so after considering T90 time, declination, right ascension, and UTC time, I found 200 gamma ray bursts in IceCube files that matched, but only 2 that had RA and DEC values within 1% of each other. In the future, I want to possibly use LIGO alongside Swift and IceCube data to trace gravitational waves back to GRBs as well. As you may remember from the original diagram showing the possible process of a GRB, of a neutrino being traced to a GRB, gravitational waves are one of the byproducts of a rapidly rotating neutron star or black hole. But as you can see in this table, those 2 more precise matches are highlighted. Next slide. Thank you very much for listening to my presentation, and a big thanks to my mentor, Dr. Michael Stamatikos. And I conducted research from work done by University of Wisconsin-Madison, which helped construct, which was a big part of the IceCube project, NASA and Tohoku University. And then here are links to where I got the IceCube and Swift data that I used.
All right, I think
I'll
that's
open
it.
the floor to questions.
Okay, let's congratulate our speaker. Good job. Well,
Awesome.
this is at least a subject that I seem to know something about, since I'm a scientific co-investigator on Swift and I also work on LIGO. Unfortunately, those 2 times of the 2 coincidences that you found were before LIGO started to work, because you were doing historical work. Yeah, so you won't be able to look at LIGO data for either of those 2 really intriguing events that you found. But it's a great procedure for going forward to, now we're LIGO's back to observing. We're in observing run number 4, and lots of stuff is starting to happen. So keep your procedure in mind for future.
Oh, sorry.
So, but yeah, that was really, really neat. So what do you think about the 2 events that you found? Do you think they're really the same? Are you going to publish it? Obviously, that's up to your mentor.
Yeah, I think there more analysis needs to be done in terms of other quality selections. But I think the nice thing is it proves the proof of concept for the Python stream to be able to. And I was very impressed with Nicholas's ability to not only understand kind of the astrophysics of those 2 different worlds, but also to be able to quite quickly put together a nice software to mine that. Yes. And as you said, this is wonderful moving forward. Because again, we don't know when GRBs are going to go off, and we could have a winner. I'm betting on that. So,
well, that would be super exciting.
Yeah. Great job, Nicholas.
Yep,
Thank you
great
very
job.
much.